Hello everyone. In this video we are going to continue our discussion on alkanes, but probably this is the first time we'll see conformations. It's the different shapes that a molecule can assume when you rotate around a single bond. The picture here is actually of a ring molecule, cyclohexane, with two groups. We won't be looking at those conformations until we look at simpler molecules. And we're going to use a point of view called Newman Projection to describe these different conformations. Let's see. Okay. All right. Let us first define conformations. It's the shapes a molecule can make or can adopt due to rotation around one or more single bonds. Okay, it's important that we do these rotations along single bonds. We've been working with alkanes, so all the carbon-carbon bonds are single bonds. So for instance, we could have a molecule that looks like this, and if we draw that, okay, so there's a molecule, 3-methyl pentane, and if I start twisting some bonds, for instance, if I could twist, if I twist that bond or rotate it, what can happen is your molecule now assume a different shape, and now it looks like this. So let me draw that. The left half looks the same, but when I twist this bond right here, I twist that methyl group, now it goes downward. The thing about conformations is that you're not changing the identity of the molecule. So these two molecules are identical, but different conformations. That's important to understand because if I ask someone to draw me, draw me 3-methyl pentane, I should be able to interpret whether that drawing is correct, whether it looks like that or whether it looks like that, etc. Now, if you think about, okay, if I'm just twisting along a single bond to get a new conformation, that's one conformation there, that's another conformation there, that's another conformation there. There's an infinite number of conformations for for most molecules, especially if you have single bonds that could rotate all the way around. So let me write that. You have infinite conformations. But what are we concerned about? We're concerned about, well, which one is the most stable conformation? Where is the molecule most likely what shape is it more likely to adopt? So we're interested in stability. Okay. And we're going to look at some rules and pick up some rules throughout the semester to discuss how stable is a molecule. Okay. Now, the molecule that I want to look at first is ethane. Very simple molecule. And what you want to do is you want to have, here's ethane without the hydrogens, and you want to go ahead and make a bunch of methyl groups, okay? Because we're going to start putting methyl groups slowly around this 2-carbon bond. Okay. But let's start with ethane. So ethane, has 6 hydrogens. I think it would be useful to go ahead and make your models so you can visualize the different conformations of ethane. Now, ethane will also have an infinite number of conformations, but there are 2 conformations that are most important. You could probably guess those two conformations will indicate or represent the most stable conformation and the least stable conformation. So here's Ethane, and if I hold it like such, maybe like this, okay, and I draw it, what do you see? Well, here, I'll hold it again, over here. What I see is these two hydrogens at the top, and I'm going to describe them in the plane of the paper. And now I see these two hydrogens kind of pointing towards us. To indicate that on a line drawing, you're going to use wedges. Like it's coming out of the page towards your eyeball. And then let's focus on the carbon on the left. See this hydrogen in the back is going away from your eyeball. And that's indicated with a dash. And you want to make the dash kind of look like a slice. Okay, with a wedge, but make it a dash. So it's triangular is what I'm trying to say. Okay, this is considered a wedge dash drawing. Or a lot of textbooks call it a Sawhorse projection or Sawhorse view. So let me reorient my molecule so it looks exactly like my drawing. Okay, and why Sawhorse? Those of you who've taken carpentry, you could put it on your table like this. Okay, and this is the I guess a tabletop where you could start sawing your piece of wood. Okay, it's like a workbench. Okay, now what about this idea of Newman projection? We have a Sawhorse projection. We're viewing it from basically the side. Okay, but a Newman projection is this: you tip the molecule so you're looking down a carbon-carbon bond. So for a Newman projection, you want your eyeball to hit one of the carbons first. Okay, and then this is the second carbon, or the back carbon. So with a Newman projection, we're going to have a front carbon and we're going to have a back carbon. Okay. On an exam, the professor would need to tell you which carbon they want to be the front carbon, which carbon they want to be the back carbon. But for ethane, it doesn't matter because it's symmetrical, right? It doesn't matter if my eyeball was on the left or on the right. Okay, but I'm going to go ahead and orient it so it looks. So we're looking at it from the pink person's point of view. The front carbon is the one I'm pointing at, and we're going to tip it like this. Now the hard part about this, the difficult part about this is how do you draw this now? Because see, there's a carbon in the back that we don't see because the view is obstructed. For a Newman projection, which is again looking down a carbon-carbon bond, we're going to use a dot and a circle. So the dot represents the front carbon, the circle represents the back carbon. And so this is my molecule, and it looks like we have an upside down Y. Look at the carbon I'm pointing at. We have an upside down Y on the front, and we have an H, H, H. Okay. The back carbon is a little bit trickier, so let me put it right in front of the camera. How do I take care of the back carbon? Well, we could take care of the back carbon by just slightly twisting to make it a little bit offset so we can see what's happening in the back. And that's perfectly fine. Okay. Now, see, do you see how my line doesn't go all the way to the dot? Because the dot represents the front carbon. The hydrogen in the back, only it's attached to this carbon in the back. So again, that hydrogen that I just drew is this one right here. Okay. So this one, this is where you have to be fairly neat to make sure that the grader doesn't misinterpret where your bonds are going. So again, we have a front carbon and back carbon. If you're using your models, okay, let's go back to the Sawhorse perspective. I'm going to point to, see, I'm going to point to this hydrogen on the bottom left. That is coming towards us. Okay. I'm going to indicate that with maybe a smiley face. Okay. My question to all of you is, where's that smiley face? Which hydrogen is it? If you imagine your eyeball where this stick figure is, and you're looking down this bond right here, well, that hydrogen is towards the ground, towards his feet. But is it to their right or to their left? Okay. If you put your eyeball right here, okay, or you could even lift up the page like this. See, that H was towards us, but from the pink person's point of view, it's to their right. To their right. And it's on the back carbon. Your smiley face is here. Oh, no. It's on the front carbon. Front carbon. Yikes. Okay. Let's try another one. Let's try this one. Let's try put a star here. Back carbon. So it has to be one of these hydrogens attached to the back carbon. And as this person looks down the bond, that hydrogen is away from our point of view, but it's to the left of their point of view. Okay. If you're having trouble seeing that, then your models are perfect, because here's your Sawhorse view, and I'm going to hold, actually I'm holding right now, the hydrogen that has a star. See, it's the hydrogen in the back. And what was my movement? My movement was to take this carbon on the left and make it the front. So look at the hydrogen I'm holding. It's on the back carbon to the left. That's why the star is right there. Okay. This conformation is called Eclipsed. Okay. That's one of the main conformations for ethane. The other conformation is we're going to rotate. We're going to rotate this back bond 60 degrees. Okay. All the way around is 360. All the way down here is 180. So it's 60, 60, another 60 to get to 180, and then another 180 to get to 360. I'm rotating the back carbon. So I'm holding the front carbon steady, and I'm going to rotate the back carbon 60 degrees. Take a look at that molecule now. That molecule, oops, right there. Okay. You notice at the front carbon, the Y is still upside down because I held it steady. We just have to now draw the back carbon properly. Whenever you're drawing, and I never said it, these are what? Newman projections. Whenever you're drawing Newman projections, give yourself a template. Is your template going to be eclipsed, or in this case, our template is going to be what's called staggered? But draw the template first. Okay. So my front carbon stays perfectly still. And you could refer to the model, or you could refer to the drawing. I rotated this 60 degrees. New projections. Take a look at my model. Take a look at my drawing. Take a look at my model right now. Okay, right now. Where is the smiley face and where is the star? The smiley face is going to be where? It's on the front carbon. Oh, and the front carbon didn't move. So it's right here. The star hydrogen was here on the left in the back carbon, and we moved it 60 degrees. So all of these hydrogens are moving 60 degrees. So if I move this 60 degrees, actually it's going to be right here in this position. Remember, that hydrogen, I know I didn't draw it, but it's hard to draw the hydrogen directly underneath this hydrogen here, right? It's hard to see because it's obstructing the view. It's eclipsed, like a solar eclipse. The moon is in front of the sun. I think that's how it works. So when I move this 60 degrees, I end up right here. Another 60 degrees, you'll end up right here. This star is going to end up underneath this hydrogen. This has a name itself. It's called staggered. Those are the two conformations for ethane, eclipsed and staggered. Because if we move another 60 degrees, so I'm looking at this H, I'll circle it. Okay. Actually, where's that H now in my wedge dash drawing? That is at the top on the back carbon, right here. So if I move it another 60 degrees, guess what? Now that hydrogen is going to be behind this hydrogen here. And we get eclipse again. We get eclipse again. Now, before we look at some other molecules, we got to discuss which one is more stable, or do they have the same stability? Well, if you think about it, if I take a look at this molecule, give me a second. Okay, there it is. If I take a look at this molecule, the eclipsed version, versus the staggered, which looks like this, one of them is more stable than the other, and it's the staggered that's more stable. Okay. Now, why is that the case? That's the case because when you have something eclipsed, these bonds are closer together than these bonds. So we would have some strain. That strain is called torsional strain. Why are we having strain though? It's because we have electron repulsion. You know that like charges repulse. Okay. So this is also going to be the same as, it's not commonly used, but you can think of it as eclipsed strain. Whenever you have a molecule with eclipsed bonds, like shown in this Newman projection, you're going to have torsional strain because we have electron pair repulsion. Of what? Of the bonds. Of the CH bonds. Now it's a little bit subtle, but let's go back to the wedge dash view. Okay, like that. So I'm talking about the repulsion between these two electrons of the bond and these two electrons. There is a little bit of repulsion. To sort of to lessen that repulsion, we go to skew it, and that bond gets a little bit further from this bond. And what is that conformation? It's staggered. So this is always going to be true. Well, for 99% of the molecules you see, staggered is more stable than eclipse. Staggered is more stable than eclipse. And when you think about the energy, right? If your molecule has more strain, more stress, okay, same idea, then it is unstable. So it's less stable. And from general chemistry, where do we see less stability? Especially when we talk about orbitals. Less stability means higher energy. Higher energy. So if you have a diagram here with E, something at this state is less stable than something in this state. And you've seen these energy diagrams before, right? This is less energy, more stable. More stable, less energy. Okay. So when we think about putting these on an energy diagram, the eclipse and the staggered conformations, the eclipse will be much higher. The eclipse will be here, and the staggered will be down here. Okay. Now, ethane was pretty simple. let me take a look at a more complicated molecule, and we're going to look at butane. So butane looks like this. Okay. Now, the problem is, a Newman projection, you look down a carbon-carbon bond, but we have actually 3 carbon-carbon bonds. 1 and 2, 2 and 3, and 3 and 4. This is where your professor has to say specifically which carbon-carbon bond to look down. And I'm going to tell us to look down carbon 2, 3. Like this. Okay. Let us draw a staggered conformation. And actually, the zigzag is actually staggered. Because if you think about, I'm going to tilt it a little bit. If you think about what the zigzag means, right, this is zigzag. Where are your hydrogens? You have a hydrogen here, a hydrogen towards us and away from us, and we have a hydrogen here and here. Why did I draw it like that? These are your methyl groups, CH3, CH3. Because what am I trying to mimic? I'm trying to mimic the tetrahedral shape of a carbon. And this will be second nature to you. Like, how did I know that my wedge and dash will be going slightly up instead of going down? Because if you take a look at a carbon, all right, that has a tetrahedral shape, look at that. Look at where my 3 bonds are, the pink bonds. One straight down in the plane, one towards us going up, one away from us going up. You know, I had this drawing here, and I wanted to add these 2 hydrogens on the left. Where are those 2 hydrogens going to go? They're going to go, obviously, in the holes, but look at the shape. Tetrahedral, right there. Take a look at the carbon on the right. It looks like this. See, one in the plane straight up, one wedge, and this one, the one I'm pointing at, dash. Okay, so the staggered position, or staggered conformation, looks like this. Look at this methyl group towards the stick figure's feet. So now we're going to have a right side up Y. See, it's this carbon right here. So I just took this molecule, I tilted it a little bit, and now my stick figure is standing on solid ground, looking down that carbon-carbon bond. In the back carbon, oh, what did I do? That's a CH3. My bad. CH3. When you draw these Newman projections, make sure that your bond goes to the atom. Okay? I see a lot of times the methyl group and they put it in the middle. So don't do this. Okay? Do you see the difference? Your bond needs to go directly to the atom that it's attached to when you're drawing Newmans. Okay? Make this an X. Look at the back carbon. The methyl group is going straight up in the plane. Again, the bond goes directly to the carbon, and it goes to the back carbon. And we have 2 hydrogens here, here. So that is staggered. The thing is, let me make that model for us. The thing is, the other staggered position is actually of a different energy. So what I drew here, zoom out a little bit, is this molecule right there. I'm pointing now at the bond, I'm looking down, so it's off to the side. Okay. If I hold the front carbon steady, I could have another staggered position like this. Okay, right? Hopefully you can tell that's staggered. 60 degrees. Oh, not 60 degrees. 120 degrees, because 60 degrees is there. Okay, why don't we actually do the 60 degrees? Because do you see how that's eclipsed? Yeah, I think that makes sense. We'll just go in order. So we're going to shift this angle. It's actually called a dihedral angle, but we'll get to that in just a bit. What I need to be concerned about now is drawing my template, hold the front carbon steady, and the eclipse is the hard one to make, right? Because they're on top of each other. So that methyl group now is right behind this hydrogen, and I'm just going to skew it a little bit. If it's very clearly not staggered, the grader is going to assume it's eclipsed, and that's what we want, eclipsed. This hydrogen goes another 60 degrees, right? So it's now, where is it going to be? It's going to be right here. It's a little bit tight, but I'm showing you that it's eclipsed by this methyl group, this hydrogen right there. And then the last hydrogen, this one, goes 60 degrees, and it goes right here. This is eclipsed. Okay. Let's do another 60 degrees. My methyl group was here. So another 60 degrees would end up being right along there. Okay. Take a look at your model. Okay. If you want to pause and make your models, that'd be great. Take a look at my eclipsed butane. Right there. See this methyl group in the back? That's this one right here. So if I move the back carbon another 60 degrees to get it to the next staggered position, how do I know that's the staggered? Take a look at the carbon I'm pointing at, the front carbon. See how the hydrogens, the bonds of hydrogens are staggered? Okay, but look where my methyl group is. It's still staggered, but it's closer to this methyl group. Okay, we're probably not going to have time to do a full analysis, but let's see if we can get the 4 main conformations now. Remember, ethane only had 2. Why does butane have 4? So make my template, and actually, when I say template, why don't we not put the atoms yet? We know that we have a staggered conformation for this Newman projection. So there's your staggered template. Where's my methyl group? My methyl group now is down here. The front carbon stays the same. Okay, and here are your hydrogens. I know I'm going a little bit fast. What maybe I should have done was ask you to pause the video and ask you to fill in all the bonds around the dot in the circle. And actually, that's what I'm going to ask you to do next. One more twist to another 60 degrees. You're going to draw the eclipsed conformation, and we'll go down the line again. Okay, there's my dot in a circle. Pause the video and draw the eclipsed. Okay, hopefully you drew the correct eclipse. The front carbon stays the same. CH3, H, H. This methyl group comes down 60 degrees, so now it's super tight. Okay, you know, our previous eclipse only had a hydrogen behind the methyl group. Now we have methyl on top of methyl. This methyl right here is in the back. Your other eclipse looks like this. Other eclipse bonds look like this. And this is eclipsed. Not in this video, but we're going to explain why these 4 actually have all different energies, different stabilities. Because take a look at your 2 staggereds. They're both staggered, okay? So they're both more stable than the 2 eclipse. That was our rule. Staggereds are more stable than eclipse. But one of these staggers is a little bit worse than the other because of some strain. These 2 methyl groups are very close together. Probably in the next video, well, yeah, definitely in the next video, I'm going to fully explain why this staggered is less stable than this staggered, even though they're both staggered.